Is the director of the Biomedical Informatics Division at the University of Virginia. As you saw from the picture that I put in earlier today, I have been popping into his office for quite a number of years, at least while we were at the same institution. So he is going to talk to us today about LIS interfaces, and welcome to Dr. Harrison.
Is the time up here anywhere?
Is
it? As long as you want. All right. Well, I hope this turns. Oh, great. Thank you. All right. Well, thanks a lot, Alexis. Let's see what we're doing here. Okay. So this afternoon, I'm going to talk to you about interfaces between LIS and instruments and other systems. And this is an area that, it's been a kind of a specialized interest for a number of years, but I'm hoping to convince you that there's actually a lot going on in interfaces right now, and it's really kind of an exciting area, maybe sort of scary exciting sometimes, but nonetheless, I think it's an area that you'll benefit some from knowing about. We're still a little fuzzy over here, but I think we can probably make it okay. All right, so what we're really trying to do here is achieve interoperability between systems. That's our key concept. And interoperability is the ability of systems to work with each other, to provide services from one system to another, and to accomplish an overall task using those services by working together. And an interface is a communications connection between systems that and a translation mechanism that allows them to share data so that they can interoperate and accomplish a task together. Laboratory interoperability in terms of the data is typically about patient registration and demographics information, orders, specimens, results, and reports. And we want our interoperability can be described as having two components: syntactic and semantic interoperability. And syntactic interoperability is the ability of systems to exchange symbols like characters and numbers or words and have those come across accurately. Semantic interoperability is just as important. That is, that when the symbols come across, do you assign correct meaning to them? And so are they understood in one system correctly? That's an absolute requirement for actually having two systems work together and share information to accomplish a task. I thought I would show this just briefly. When we think about interfaces, today we're going to be talking about information kind of at a high level. We actually assume that devices can exchange information accurately to a large extent, and so all of these layers down here, the wiring, things like Ethernet, routing of packets and transporting them and verifying that they get from one place to another accurately, which is most of the time TCP/IP now. This is low-level transmission standards, and we can pretty much assume that those are going to work, or that there's a technical problem we need to work out. And what we're going to talk about is the structure and content of messages that healthcare systems send to each other. This is at the application and presentation layer, things like characters, lines of text, delimiters, and fields in messages. And then the data model, what message contains, what information it contains, the data elements, and the semantics of the message. Now, those layers are where syntax and semantics happens, and this is where the standards we'll discuss today, and that you've already discussed briefly, operate. Data standards like those from the HL7 organization, CLSI, which those standards used to be called ASTM before 2001, and still are referred to as ASTM sometimes, and the IHE standards organization and so forth. In fact, HL7, or Health Level 7, the 7 in the name actually refers to this seventh layer of the ISO networking stack. Okay, so to start, let's kind of deconstruct the logical components of an interface, and then we can use this, we can keep this in our head as we talk through the rest of the slides. So what we really want to do, the task here, is to transfer data from one database to another, for example, from an EMR to a laboratory. That might be patient data, might be an order, and so forth, and then transfer lab data, which might be an order with associated results, back to the EMR database. And to do that, you need software, and that's what these represent, that can extract data from the database and then construct a message. Now, the message that gets sent from one system to another needs to be understood by the other system, and typically the data in these databases won't be represented exactly identically. So there'll need to be some transformation done on certain data elements, maybe not all, but some data elements, in building this message. And these transformations are typically held in a mapping table, and there are mapping tables on both sides. And so a mapping table will take the form of data that is in this database and the form of the same data elements or the corresponding data elements in the other database and match them up so that data on one side can be transformed into a representation that's meaningful on the other side. So message construction will go on with the data that's pulled out in combination with the mapping table, and then the message is sent from one side to the other. On the other side, the message is parsed to take it back apart, take these data elements, and if they're all understood, insert them into the database. And it happens in reverse with the message going the other way. Now, in addition to sending the data across to the other system, you'll also write the message out to a transaction log, whichever way it's going. So a transaction log is kept on both sides, and if there's a problem with communications, this transaction log actually contains the messages, so it can be accessed if need be, and the messages can be resent. So nothing is lost even if there's a communications interruption. If a message is received by a system and there are data elements in it that it doesn't understand, or there are aspects of the message that are problematic, it can't insert things that it doesn't understand into its own database, but rather than throwing it away, it'll write it out to an error log. And so there are error logs on both sides too. These error logs can be reviewed, problems can be corrected, and then messages can be resent. And so when problems occur, the transaction and error logs on both sides can be compared, problems can be worked out, and then messages can be resent without losing anything. And so those are the basic logical elements that we're going to be talking about: the databases, the message construction and parsing software, the logs, mapping tables, and communication, and the messages themselves that go between the systems. Let's see. Okay. Now, I thought I'd spend a minute talking about why these interfaces are important, now that we have sort of defined what we're talking about. Well, the value proposition of EMRs and why they're being installed depends largely on interoperability between systems, interoperability between EMRs, and interoperability between EMRs themselves, and interoperability between other medical systems in an environment and an EMR. So the EMR can be a receptacle and an aggregator for medical data. So interoperability and interfaces is important for EMR value. Now, the high-tech incentives, the high-tech that's part of the ARRA legislation, is incentivizing the installation of electronic medical records, and that, particularly ambulatory medical records, and that's increasing the number of laboratory clients who have EMRs. It's estimated that the number of ambulatory ambulatory practices with EMRs is going from less than 25% in 2009 to greater than 80% by 2016. And this increases, or this puts EMRs in many environments that we might have been able to communicate with paper or faxes in the past. And of course, once those EMRs are in place, they're going to want electronic transfer of data, and as a matter of fact, they'll have to have it, because in order to satisfy meaningful use, they're going to be able to need to do physician entry of test orders and electronic receipt of test results. CPOE and lab reporting were a menu item that is an optional selection in Meaningful Use Phase 2, but are actually required, at least for a % of laboratory tests. I should have said Phase 1 of Meaningful Use. They were a menu item. They're required in Phase 2. In addition to, and so basically that's going to mean that there are a lot of people who don't currently have interfaces or practices that don't have interfaces that over the next several years are going to want them. Now, in addition to new interfaces, the data content of interfaces is essentially being upgraded as part of the meaningful use activity. And so in order to qualify for meaningful use, the messages that you send and receive are the standard that you're supposed to use for this has been developed in HL7 2.5.1, which is actually a little more advanced than the most widely installed version of HL7 at the moment. And there's a requirement to use LOINC and SNOMED codes to a certain extent in these messages. And that also is going to require an upgrade to interfaces. So we're looking at a situation over the next several years where there will be a demand for new interfaces and a demand for upgraded interfaces for our clinical clients to meet meaningful use. Implementing and upgrading interfaces has a substantial financial impact, and that's one reason why interfaces are important right now. And in fact, even just in terms of medical care, interfaces between systems are ubiquitous in medical environments, and they're really the glue that holds the system together. And this is not University of Virginia, but it could be a reasonable description of most large healthcare or large provider organizations out there now, where you essentially, all these boxes represent different systems that are sharing data with each other. And you know, the boxes that are different colors are different classification or different types of systems. So the peach is clinical systems, green is billing registration, blue is financial systems, and so forth. Some of these are connecting directly to each other, but many of them are actually connecting to this central system that I'll talk about a little bit later, called an HL7 interface engine. And in fact, some of the systems, this is a financial data warehouse, has actually been drawn in. Obviously, this is a dynamic environment because by the time you print these out, they're out of date. So our systems are basically networks, are fairly complex networks all connected together by interfaces. Now, let's simplify that a bit and focus on the kinds of interfaces that are of primary interest to the laboratory. And as we go through the talk, I'm going to refer back to this image to help us orient to the sets of interfaces we're talking about. But what we've got here is interfaces that are within the laboratory, primarily related to instrument connectivity, interfaces that are within our local health system, and then interfaces that are outward-facing to entities in the community. And actually, these are supposed to have little sort of pink fuzz around the edges of them. You can see it better over here. And that represents encrypted connections or potentially a virtual private network. So we'll talk about each of these classes of interfaces separately. So first, instrument interfaces in the laboratory. These connect instruments to the laboratory information system. They may be a direct connection to the LIS, or an instrument manager may intervene. As you saw here, instrument managers are sometimes referred to as laboratory middleware. The point of care manager that I showed is kind of analogous to this in that it manages connectivity to point of care devices, and they're docked periodically to it, and then it communicates with the LIS. These instrument managers may connect to multiple analyzers and then manage them and then transfer information to the LIS. Instrument interfaces can be unidirectional or bidirectional. Almost all interfaces now, instruments in major labs, are bidirectional. With a unidirectional interface, basically you need the accession number and what test you want run. You put the specimen on, it runs the test, gets the result, and then basically sends the results to the LIS one time. And once the result is sent and acknowledged, it doesn't maintain a lot of data locally. Bidirectional interfaces are more comprehensive. They receive and store orders from the LIS, so the communication goes both ways. Orders are stored. Typically, they're used with barcoded samples, so the instrument reads the barcode, uses that to retrieve the appropriate order, and then executes the test based on that order. The results can be stored locally and sent to the LIS, and they can be results can be maintained for a period of time locally before they're purged, so that if there's a need to resend, you have the ability to do that. Now, bidirectional interfaces raise an interesting situation if you have multiple analyzers that run the same test, and it's not unusual for large labs to have multiple analyzers and divide the workload across those analyzers. And so how do you know how do you get the right order to the right analyzer? Well, one thing you can do is send all the orders to all the analyzers, basically broadcast the orders, and then the analyzer that gets the test or gets the specimen knows what to do with it. But that creates a situation where you have to purge the completed orders from other analyzers that don't know the order's been completed. That can be done. But typically, analyzers will now query the LIS once they receive a specimen to get the order for that and run it. And that avoids the purging problem. However, that means that your interface needs to be fairly quick. If the LIS responds slowly to that query, then you're going to have throughput issues. It'll slow down your analyzer. And so those are things to look at in implementing these interfaces. Now, these interfaces can be standard or they can be proprietary to the instrument vendor. If they're proprietary, they essentially function as an instrument driver in the same way that a disk driver or some other equipment driver, peripheral driver on your desktop computer might. And the data that's transferred can be encoded in any way that the vendor wants. Typically, though, these the interfaces are standard interfaces, and the majority of them are CLSI, which was previously called previously out of ASTM, when NACLS, which was ASTM affiliated, turned into CLSI. Then this became a CLSI standard. So you'll see that in many labs, the majority of instrument interfaces will be the CLI interface. There are also HL7 interfaces for instruments, and there is a new HL7-based profile that came out of an instrument vendor consortium called the In Vitro Diagnostics IVD Industry Connectivity Consortium, or IICC is the name of the consortium, working through the IHE Standards Organization. And that, in the last, I guess, ending about 6 months ago, they put together a new HL7-based profile for instrument interfaces. And the idea here is to make connecting an instrument to the LIS or to an instrument manager more just drop in and plug and play. Now, from a pathologist perspective, these interfaces are relatively plug and play already, because it's up to the instrument vendor and the LIS vendor or the instrument manager vendor to make it work when you purchase the instrument and you have the LIS. However, improving these standards will make the interfaces less expensive and less prone to problems. Okay, I'd like to turn now and talk about local system interfaces, and these are going to be almost all HL7 interfaces, and they may be directly from the LIS to other systems in the environment, but more commonly they'll go through an HL7 interface engine, which will then distribute them out. And by the way, I should include financial systems here. It was late, and that should have been written right in there, because those are important as well. So typically you'll have the LIS interface to the interface engine, which actually may be multiple interfaces managed by this, and then the data will be distributed out appropriately, or the HL7 messages will be distributed out to these systems. And so I'd like to spend a little bit of time talking about HL7, and I know there was an introduction to HL7 this morning, and you also talked about some other standards like LOINC and SNOMED that we'll refer to briefly, and so I'll go through this fairly quickly since you've had an exposure to it already. But HL7 is Health Level 7 International. It's an ISO-affiliated standards organization, and it goes through an ISO-like or an ISO-defined process for creating standards. If you're ISO-affiliated, you have to use their methodology, which is to some extent slow and cumbersome, but it also makes sure that everybody gets to review and comment. And so these standards are developed by people in the field who are interested, including vendors, large laboratories and other users. There are teleconferences and meetings multiple times a year. It can actually use up a fair amount of time because, in fact, there's a lot of work to do with this. Draft standards are developed. The standards are put out for comment. Comments are responded to, and all comments have to be responded to. The standards are then put out for vote once the comments have been dealt with. If they're voted against, a reason has to be given, and those reasons have to be dealt with, and ultimately, once they're voted in, they're accepted as a normative standard. So all ISO organizations work that way, and HL7 is one of them. So the HL7 messaging standard is a framework for messaging between healthcare applications, so it runs sort of at level 6 and 7 of the ISO stack like we were talking about. It's been around for a long time. The version 2 was released in the late 80s and became widely deployed. The most widely deployed now is actually version 2.3 and 2.3.1, which were released in 1997 and I think 1998 for 2.3.1. The current version is 2.7, so there's been a fair amount of development of the HL7 version 2 standard, but most of our deployments are still relatively old. So actually a lot has happened. There's also a version 3 of HL7 that you may have heard of that was released in 2003 and 2004. And I'll refer to this briefly as we go through the slides. It used to be that you had to be a member of HL7 to use the standard, which in most of our cases meant that our vendor was a member. And then they would write the standard into their systems, and then it was used at our sites. HL7 last month has announced that they were going to release their standards for no-cost use. And so the standards are going to be a lot more accessible in the near future. Now, this standard is a framework. It's not a complete specification of everything in a message, which means that you have to specify a number of aspects of the message locally. You can use the framework, and the framework helps, but a lot of what's in the message are local definitions, and so it's not plug and play. You can't just connect two systems together with HL7 and have them talk to each other and know what they're saying. In a sense, it's almost like they both speak audible language, but one is speaking English and the other is speaking German. And you have to find a way, you have to handle the translation, or your consultant does, and vendors. Okay, so version 2 defines a very large number of message types that are related to particular medical events like admission, registration, discharge, transfer, queries, orders, results, clinical observations, and so on and so forth. And it defines a transaction model for how systems should send messages to each other. Who gets to send a message first, under what conditions, associated with what event, what kind of message should be an acknowledgement of that message, if there's an error condition, what messages are sent and what's written out, and that sort of thing. So you've got a transaction model and message types, and then for each message type there's a message structure. That is, what data fields are present in that message. Now, but you're not required to use the data fields, just have them in the message. They can be empty. And their contents, to a large extent, aren't specified either. So you get to put what you want in there. You can put the patient name in the way you want. Although the field is supposed to contain the name, you could put last name first name first, and that sort of thing. So, and part of the reason for that is that HL7 version 2 is really pragmatic, and the framework development predated a lot of the work that happened in terminology standards that happened actually in the 90s and the early 2000s. As we said, it was released in the late 80s. And therefore, those standards weren't available to specify. So, just briefly to take a look at some messages, and I think you've seen a little bit of this already. This is an admit message, which is a relatively simple one. And the parts of the message, basically the message is lines. And these indented lines actually go onto the back of these lines. So this is a line that goes way out here. This line goes way out here, and so forth. The messages, the lines are called segments. And each segment begins with an abbreviation indicating what it is. So this is a message header, this is an event, This is patient identification, next of kin, patient visit. And each segment contains information that's about its topic. The segments are delimited. They have delimited fields. In this case, the delimiters are the vertical bars. And so in between the vertical bars are the fields. So this is field 1. It has a 1 in it. That's an empty field, field 2. This is field 3, which goes way across to here, field 4, and then field 5 here. Now, within a field, which is supposed to have a certain kind of data, you could split up that data into individual data elements called components. And so our second delimiter character here is a caret. And so these are different data elements. And in fact, you can split it up a couple of more times. And so you can see here the hospital name and then a designator has a tilde here as dividing this component into subcomponents. So that's basically the structure of an HL7 message. Segments, fields, delimited components, and delimited subcomponents. This is a result message. We saw the MSH, PID, PV1 before, so those are grayed out. What's different here is that an ORC and OBR provide information, or they carry information about the order, and the OBXs, I should have indented that one. The OBXs carry observations or results. The result of a lab test is a kind of observation. And so you can see that the order is for a basic metabolic panel, and the OBX has a number that actually is the sequence of the OBX. It has the data type, which here is a number, and the third field is the name of the test, so the test code and the English expansion of it. Here's the result, units, reference range. The next thing is a flag, and so if you have something that's high, like a high glucose, you'll get an H in that field, otherwise it's empty. And then some other fields out here. This is the status, F for final, and so forth. Yeah, this is wrapping differently. Hopefully we won't have too much trouble with that. This one came across okay. This is an eye test. Actually, you don't really need to see this in detail. This is supposed to represent a textual result. So previously, the key thing about this message is that each test is named in a field where basically the test name, the code and the name is in the field, and then the result here and here is in a field, and the result is the only thing in the field, and it's a number, so it's easy to interpret. This is a little bit different animal. Here we've got OBXs, and they're numbered sequentially all the way down to 29, and that's not the end of the report. It actually goes down further. This is a radiology report, but a pathology report would be similar. And so what you have is the data type is TX, text. This is the name of the test, which is the name of the, I guess this is a chest x-ray. Yeah, single view chest. So that test is repeated over and over and over again because this is one report on that one test. And then field 5 in OBX is the field that contains the results, and you can see it says preliminary. This is a preliminary report and should be viewed as preliminary and may be appended in the final report. And then there's the count number, order number, and so forth. What we've got here is a report that's fractioned into lines. And each line gets its own OBX, and that text goes into OBX field 5, the result text. And this is typical for how reports are handled. Textual reports are handled in HL7, and this is one reason why we have a problem with how reports are transferred over to EMR systems and why they don't display in ideal ways, because this is just text characters. There's no information here about font. There's no, bold or italic, page margins. There's no really good way to do tabular data if you want to show a table. So because of our transfer mechanism, we're really limited in what we can do, and I'll talk a little bit more about that in a minute. Okay, and then for whatever message we're using, we can look up, or any message we're interested in, we can look up that message in the manual for the version of HL7 we're using, and we'll see that for a results message, it's supposed, and some of these are optional and some are required, and I've left that out for for simplicity. But there should be a message header, patient identification, demographics, and so forth. Here's the common order and the observations report, which is the detailed order information. You can have notes and comments, that's optional. Here's the OBX, that's the result, and so forth. And then for each one of these segments, so the table defines the segment construction of a message, and for each segment, there's a definition of a segment. And these are the fields in sequence. So remember, the first one was set ID is for this set of OBXs, is it the first one, second one, third one? So this it's sequence. The field 3 was the observation identifier, that's the test name. Field 5 was the observation results, then the units, reference range, abnormal flags, and so forth. And so that is how the, and what it, and this, in addition to saying what should be in the field, it will tell you something about whether the field is optional or not. It'll give you the data type, string or coded entry or number, and then a maximum number of characters. And notice the observation results, field 5 can have 65K in it, so it can be very long according to the HL7 specification. You could get a whole report in one segment with that, although if you go over 65, you won't be consistent with the specification anymore. So, but the actual contents within the fact that you need to use text or a number and the number of characters isn't specified. And so it can vary from site to site. And so this is field 3, the name of the test. This is field 5, the result. And you might have the ABO group, which these sites happen to use the same English name for, might have different codes. The result, which these sites happen to use the same English name for, might have different codes for a categorical type result. This is one thing that the LOI and LRI, actually the LRI, the lab reporting interface, is trying to get at with the use of LOINC and SNOMED. So the issue here is that if another system doesn't represent these tests in exactly the same way, you need to do a mapping and translation. In the LRI, this would be, rather than a site-specific identifier, you would have potentially a LOINC code here, the English description here, and then in a third component you would have what kind of code it is, so an indicator of the LOINC system, indicating that that's what you're using. And then out here you might have SNOMED codes for blood types, or in microbiology you would have SNOMED codes for organisms, and then you would have the text associated with that, and then an indication of what coding system was being used. Okay, so I mentioned that the idea behind these initiatives, which were carried on by mainly people drawn from the HL7 Standards Organization, working in cooperation with the Office of the National Coordinator for Health IT, standardized HL7 interfaces for lab orders and lab results. That standardization, that specification, is based on HL7 2.5.1 with additional constraints on fields, including LOINC for test names and SNOMED for non-numerical results. And as I mentioned, that most interfaces are 2.3. 2.5.1 is fairly compatible with 2.3, but that will still require some work to get these interfaces either upgraded or transferring the right data. And if you're interested in more information about this, the description of lab orders interface and lab results interface, the work that was done, specification and so forth, are available from the SI Framework Wiki at the address there. Okay, I want to come back to this issue of textual reports because that's something that crops up fairly commonly in pathology. It really affects everybody. Basically, in a routine OBX segment, it's just characters, indications of characters without any style or layout information, and the reports are also fragmented into multiple lines, typically. Now, there are ways that style reports could be sent. And there are standards. Now, of course, you need to use an open standard, or ideally would use an open standard for a styled report. And there are standards that are available for that. including the HL7 version 3 clinical document standard, which is XML and allows structured data as well as marked up data for display. So you could create a report in this, and there are ways to send this as an HL7 version 2 message. You can either pack the whole thing into OBX field 5, and you can encode it in a way that it can be packed there. Now you may have characters in there which would otherwise serve as delimiters in HL7 messages, which would cause trouble, but there are ways to escape those. It just means that your interface is more complicated. You could potentially attach the reports to an HL7 message as a MIME attachment, multipurpose internet mail extension. And this is the same mechanism that email attachments use over the internet. And HL7 interfaces can support this, but that requires an interface that will support it. And it also requires a sending system that can create the attachment and attach it, or create the message with the attachment, and a receiving system that can read the attachment and know what to do with it. So there are ways that the problem could be solved. I will say that one of the things that we want our information that we produce in pathology to do is we want that information to be we want it to be meaningful to the clinicians, but we want it to be processable also so that rules can operate off of it and so forth. And so we don't really want a report that's kind of dead-end text. It's only available for reading. We need an accurate display, but we also need to be able to provide data elements for processing. And so what we would like is a data transfer mechanism that includes both structured data and human readable data. And then I'll point out that obviously the sending and receiving systems both have to be able to handle whatever strategy we go with here, and the receiving system needs to be able to display the results. So if you send an RTF report, the receiving system needs to be able to handle RTF, obviously. If you send PDF, it needs to be able to handle PDF. So multiple layers of software have to be kind of synchronized all at once to make this work. Okay, now I mentioned that HL7 introduced version 3 in 2003 and 2004, and the goal for going to a very different strategy for data transfer was really to, they recognized the problems that existed with HL7 version 2 and the lack of standardization of those interfaces, and they wanted to to standardize the interfaces with greater control so that you would be able to have interfaces could be more drop-in. Which would, the idea was to substantially reduce the interface development time and the cost of implementing an interface, and also be able to test an interface to see if it conformed with the specification automatically, which, because a lot of the message is locally defined, you can't do that with current HL7 version 2 messages. They also wanted to support, modern data communications, web services, and that sort of thing. And to draw all messages. Well, what they did was they created a reference information model that described medical practice, and all messages are drawn from and reference to the RIM. So there's a shared information model. It includes all content of all HL7 messages, defines down to the data element how the data element should be represented, including coding systems and so forth, and it provides a very consistent strategy for messaging. The reference information model, or RIM, really defines things as entities and acts. And these are the data classes that and the data attributes that describe different entities and acts. And entities can have roles. So a person might be a physician in one role and a patient in another role, and entities with roles participate in acts. And that describes that's a structure to describe a lot of medicine. In addition, there are a set of classes that relate to messages and message structure, and there are structured documents. Well, this is theoretically great, but it turned out in practical implementation to be really complicated, and the uptake since it was released has really been limited. The greatest impact has actually been in the clinical document area, and so the development of the clinical document architecture CDA documents have had some impact in certain specialized cases. And one good thing about them is that they combine structured and human readable data as a combined XML construct. That turns out to have been a very useful approach. Continuity of care documents, which you may have heard about, is a way to package up a disparate set of medical data that needs to be transferred between one system to another. They were actually developed to transfer information on a patient from one EMR to another EMR in order for the patient to be cared for at another site, but could be used for reporting, including integrated reporting. So CCD documents are a specialization of the clinical document architecture. But, like I said, this turned out to be unwieldy, and they were complex in practice, required special modeling tools and so forth, and so few interfaces using HL7 version 3 exist. Now, in the last year and a half, a new effort has developed that is trying to build a simplified messaging structure on top of the RIM called Fast Healthcare Interoperability Resources, and it's pronounced FHIR. You can get information about it here. This is an HL7 project now, and it's basically defines a set of resources. And resources are things that are, concepts in the medical world, like physician, patient, test, specimen. So each of these has a set of attributes that describe data about it. And the messages are aggregates of these resources. So a physician, patient, test, order, specimen, you might package that together in an order, and then you would package part of that along with the result back, sending it to the physician. You can look at these. They are represented in XML. You can look at them and read them, so they're individually understandable. And they contain both structured data and human readable data, and the human readable data is formatted in XHTML, so an existing standard, and it can, cascading style sheets can be used with it to make it, to visualize it the way you want and so forth, or visualize it differently in different display environments. So it has some interesting things about it. It uses Internet Standard Communications, HTTP, like the web, Hypertext Transport Protocol, and Atom is a mechanism for packaging the resources into messages. And it's currently in draft for comment, so it's going to be a while before this is out available for use. But a couple of pilots have been tried out. And it has the potential to yield drop-in interfaces with good visual formatting of reports and machine-readable structured data without being overly, at least without being as complicated as the original version of HL7 version 3. So that's going to be something to watch. Okay, to put in an interface, you basically work with and manage vendors of the systems on both sides. So basically, you need to know what HL7 version 2 message set you're going to send. You need to look at the data element representations in both systems, use that to build your mapping tables, what needs to be translated from one system to another, implement your communications within the vendor frameworks, and if the vendors have connected their systems at other sites, they have a software framework for making the connection. It's just that the mappings and so forth, some of them are going to be unique to your site. Then you need to test the data transfer using both correct and erroneous data, or data that you don't expect, so that you can see how the interface performs. And you also need to validate the data display in downstream systems. So in the requirement there is that you look at the data display in the first downstream system where clinical decisions are made and validate that the data is displayed in a way that is consistent with the meaning of the result, and that can be used effectively clinically. Typically developing, I think 2 to 4 weeks, that's quoted, although that's probably optimistic, and $5,000 to $20,000 for an interface. Many places put in an HL7 interface engine. I referred to that briefly on an earlier slide. These are software and hardware, basically computers, that will connect to multiple back-end or multiple systems, and you connect to that directly. And so the only thing you have to connect to is the interface engine, and you can work out the details of doing that. And then the interface engine The reason it's an engine is that it handles data mapping and it handles message processing and message routing. So it sends messages to the right places and it transforms messages in appropriate ways based on rules and scripts. These are typically run by the healthcare enterprise IT staff, and they cost upwards of several $100,000 plus staff to maintain them and operate them. And that's what this is. So it mediates between multiple systems rather than having all these systems have to connect to all the other systems. Many of the systems will just connect to the interface engine, and then it can distribute out their data to the other systems that need it. And that helps manage the sort of interface explosion problem. Okay, I want to say a few words about interfaces going to outside entities, like including reference laboratories and providers in the community. Reference laboratories will generally provide an HL7 interface and work with you to connect your LIS to their system. Physician offices and hospitals and clinics that may be affiliated are more of a problem, and these are the ones that are actually installing the EMRs now and may need EMR upgrades and so forth. There are increasing numbers of these that you need to keep track of and that are going to be interface issues in the future, and it probably, depending on your environment, it may not be practical to link to all of these individually. And there are a set of companies that have been referred to as laboratory provider link companies, or LPL systems, that will manage the interfacing with these external community folks. Now, typically what happens is you make an interface to their system, and then they will handle the interfacing to the various providers in the community or hospitals that you need to link to. They can place the device locally at your site, but manage the external interfaces. Or it could be potentially offered as a vendor service. So you link to them at their site, and then the other places, the community providers link to them at their site too. Reference laboratories actually use these vendors, and so the reference laboratory link may be an LPL style link, and in fact some reference laboratories will handle your community connections if you want. If those community providers will agree to send their esoteric testing to the reference laboratory, they can send their regular testing to you. The data will flow over the link to the reference laboratory, which will bounce the regular, the routine testing back to you. And that may be a somewhat less expensive way to do local links if you can have everyone agree to have a strategy for testing. And of course, internet communications require data protection. Typically these connections will be encrypted. You may do a periodic transfer that's encrypted, or a virtual private network is a persistent encrypted link that connects two networks together, or connects an external system to a network so that they can communicate on a continuous basis. This is generally handled by the enterprise IT folks. And there's a fair amount of negotiation you need to go on with them. Typically, everybody involved, including the client in the community and the LPL, if there is one, will assign business associate agreements that make it clear how they're going to manage the data and what the security policies will be. Interfaces do need to be maintained. Typically, you will immediately respond to problems by, this is often an issue of looking at transaction and error logs and comparing them, correcting and resending failed transactions. Typically, you will do a daily verification of the interface operation, check to make sure they're up and running. You'll check the error in transaction logs, even without a call, to make sure that there aren't things being written to the error logs, stuff like unknown physicians and so forth. Things sneak into systems sometimes that haven't been communicated to the other system, and you need to watch the error log to catch those things. Failed transactions can be corrected and resent. You may make latency measurements monthly. This is how long data takes to cross the interface to see if there's an interface data transmit, whether it's performing reasonably. Then there's an ongoing editing and testing of new mappings, including physicians, test catalog updates, locations, etc. And then biannually, you'll typically revalidate the data transmission and the results display, and also do this after changes and upgrades. There are a number of challenges associated with interfaces, including if you have multiple client EMR systems, you're going to have to synchronize your test catalog across all of those, potentially to their internal representations, and that can cause your mapping tables to explode. So you have to try to keep track of that and standardize things as much as possible. If you need to convert your test catalog to LOINC, that effort is going to be a significant effort, as I think you've probably discussed earlier today. Managing the progression of reporting to structured data and better report formatting as those techniques become available will be an issue. Trying to identify patients across multiple client EMRs when a patient may change is a problem that occurs occasionally. And then maintaining downstream system validation when you're not responsible for those systems. So you need to be cognizant of when they make upgrades and changes in their systems that requires revalidation. Distributing reports across multiple systems and to physicians in different settings in multiple systems, and also the necessity for institutional collaboration on security policies. So I'll leave you with just these take-home points. System interfaces are a crucial glue that holds the entire information environment together. There are a variety of interfacing challenges that labs are going to be facing over the next several years, including increasing numbers of clients with new and varied EMR systems and regulations that require potentially upgrades of current interfaces. The software and information design of interfaces is well established, but as we've discussed, it's not plug and play. Additional standards development are underway, but interfaces take a fair amount of work to deal with because of this issue right now. And then there are effective strategies for dealing with these things, but it does cost something. It takes a fair amount of effort, and you're ahead of the game if you can plan with an awareness of interface basics and make sure that you have mechanisms in place to try to avoid or dodge problems, take advantage of new capabilities as they become available, and use your interfaces as effectively as possible. I don't know if there's time for questions, but if there is, I'd be happy to respond to anything.
Do you guys have any questions for Dr.
I'll make it low-key. Just wondering where in your interfaces, interfaces to an HIE and state public health or public health reporting for cancer reporting or electronic laboratory reporting would fall into your diagram?
Yeah, so most of these questions actually have multiple possible answers, and it may differ from site to site. I think most places are actually thinking about interfaces straight from the lab system to do that, as opposed to, for example, from the HL7 interface engine. You could take that off the interface engine if you wanted, but I believe that most places are probably going to do a direct lab interface. Virginia's HIE is still being discussed in terms of the standards that are going to be used, so it's a question that's probably going to be out there for some months for us still.